Let's study accelerated motion due to gravity, which is also called free fall. So essentially, it's just a physical fact. As long as you're on Earth or in any planet, you're subject to the planet's gravitational pull, and this force is called weight. W equals mg. This is weight. And g is acceleration due to gravity on Earth. So why do I say on Earth? Because if you were on the moon, your weight will be your mass times the moon's gravitational acceleration. On Mars, Pluto, and other planets, the gravitational acceleration g is different. And why does gravitational acceleration exist? We'll get into a more deeply when we study universal gravitation later. For now, just know that if you're on a massive celestial body, there is a mutual attraction between you and the body. Because Earth is so massive, the force it exerts on you is significant, and that is what we are calling weight, while the force we exert on Earth is negligible in comparison. The net force on you is m times g. So by Newton's second law, F equals mg also equals ma, so A equals g. In short, on Earth, you experience a gravitational acceleration g downward towards the surface of the Earth. Usually, if the problem doesn't specify, take g equals 9.8 meter per second squared. Sometimes it's given as 10 meter per second. The direction is always toward the ground. And now, the common problem types are quite straightforward. Let me just outline a few. So first, you throw an object upward. And second, you're dropping an object, let's say from a building, well, that's forbidden, but you're dropping something from rest. Or you're throwing an object downward with an initial acceleration. It's not throwing it at rest. Basically, these are all the main scenarios: throwing up, dropping from rest, or throwing down. And the key is still using our formulas taught before. V final equals V initial plus A times T, and X equals V initial times T plus 1/2 AT squared. But here, acceleration is temporarily replaced by g, gravitational acceleration, and you must pay attention to the signs. For example, if you take the positive direction up to the sky, so your acceleration g would be minus 9.8 meter per second squared, and you should pay attention to the signs here. So we can try to give you some examples. You see, a projectile is fired vertically upward at an initial velocity of minus 89 meter per second. So how high will it rise? How long will it take the projectile to reach that height? Think about a key question here about the highest point. So what characterizes the highest, the maximum height? Is the displacement zero at the highest point? No, it has risen to a certain height. Is acceleration zero at highest point? No, acceleration is still 9.8 downward. So is the velocity zero at the highest point? Yes, that is correct. At the peak, velocity is zero. So at the highest point, its V final equals zero. And using V finals equals V initial plus AT, we can substitute, plug the values inside. V final equals 0, and initial velocity is 98, and acceleration is minus 0.8 meter per second squared times t. So we can get the time is 10 seconds. It spends 10 seconds to reach the peak. And then for the height, displacement equals V initial times t and plus 1/2 times AT squared. We can plug the values inside, so its initial velocity is 98 times time 10 plus 1/2 times minus 9.8 times 10 squared. We can get the displacement, which is the maximum height. So this is a very typical projectile question. You must be aware of the fact when you or the object reaches the maximum height, its final velocity will be 0, and that's the only reason why it stopped moving for an instantaneous instant. And that's how you find the maximum height. And if you master this very well, later topics like horizontal and angled projectile motion will be way much easier. So the key question is about how you analyze the point at the maximum height. And we can also briefly discuss graphical analysis of motion. If you drop an object from a height, its speed increases as it falls because acceleration is downward. If an xt graph, position versus time, the slope represents velocity. As objects falls, the slope becomes steeper, meaning velocity increases. So your xt graph will be looking like this. The slope will be higher and higher, meaning the velocity increases. If an object accelerates from rest and then moves at a constant velocity and finally decelerates to stop, the velocity time graph would show velocity increasing, constant velocity, and decreasing. This is just like a car speeding up, cruising, and then slowing down, a very common real-world scenario. And this is essentially motion under gravity, which is free fall. It's not difficult once you grasp the previous kinematics section. And hope you can learn it very well. So let's just stop here, and next lesson we are going to learn relative motion. So see you next class.